Well, good morning, everybody. Welcome to physics. And today we're starting to talk about vector addition. And if you didn't notice yesterday, you all had the same deck for your lab, and you all ended up in the same spot, right? But did you go the same way? No, you didn't. You did not go the same way. And the reason why we did that was to express to you this point right here. Order in which we add vectors doesn't matter. Okay? So there's a lot of flexibility with vectors, which makes our math a lot easier. So you're in control of this again. So it's nice to be able to do what you need to with the math. So vector addition, remember scalar has just size. Vector has size and direction. And just to kind of look at the notes, if we add this plus this, okay, we're going to get this, right? But if we add this plus this, we're still going to get this. Does that make sense? So it doesn't matter what direction or which way you add these things. And you guys added them, 6 different ways yesterday in lab. And you all still got to the same spot except for one group, I think, messed up a little bit. Which is fine. Okay. So if you look a little bit further down, and these notes will be on Moodle. I just got them uploaded here. So the way that we add vectors is we add them from head to tail. Okay. So what that means is you start and you draw your first vector, and as you can see, this here's the head of a vector. This would be the tail, which that's pretty easy to figure out, right? But now I told you, you can't forget. And then the next vector that you're going to add, you put the tail at the other head, and that's the way we add them. Now, kids get screwed up because they think then the resultant of the addition, or the added vectors, is also head to tail. But as you can see here, by example, when you actually finally add and draw the resultant of the two vectors that you added, or however many vectors you added before, you don't do that head to tail. You start that tail of the resultants at the origin, and then the head would be at the final position. Okay, so when you're putting vectors together, you add head to tail, but the last vector that shows you what the summation of the vectors is not head to tail. It starts at the origin and at the head of the last one. Okay, there are a couple other ways to do vectors. Like you can do this and this, but this is really hard. So this would be the resultant in the middle. Another way is the parallelogram method. So you would add. So it's really doubling up on that, and then double up on this one, and then that would be the resultant, but none of those are very good. In fact, the graphical method of adding vectors is not very good. You need to be able to show that so you know what's happening. And this is kind of what I've been doing is this graphical method. What we're going to concentrate on is something other than graphical. And this point right here is very important. All vectors can be split into 2 or more vectors. And the reason why we want to do that is so we can make a right triangle. Okay? So, for instance, this is the vector that we're going to talk about. Now, if we were going to give or do some math with this vector, what we would want to do most of the time, unless there's, no change in one of the components of the vector, is we want to split this up into a right triangle. Okay, so if you look at this, you'll see that this piece right here and this piece right here are what I made or drew to define this vector so that we have what I call all x's and all y's. So this is the x side, right? Because it's just like on any graph, the horizontal is the x, and then the vertical is the y. So we have a right triangle there. And now we can do more math with this vector when it's split up like that. And this one, for instance, I split up into an x here and a y here. Okay? So the reason why we want to do this is, especially in projectile motion, we'll find out that an acceleration happens due to gravity, but that only affects the y stuff. And the x stuff is actually unaffected by the acceleration due to gravity. And there are a lot of reasons why we want to split our vectors into x and y components. It's not just gravity, but it's anything that we need to analyze in two components rather than just one. I don't think I explained myself very well that way, but you'll see as we go on. And why do we use right triangles? So we can utilize this math called right angle trigonometry. Okay, so how many of you are familiar with this? Sure, the calculus people. I don't know, maybe pre-calculus. I don't think you're into pre-calculus yet, but this is what you have to memorize, is this word, SOHCAHTOA. SOHCAHTOA, okay? And the reason why you need to memorize that is because it tells you your formulas that describe ratios of triangle legs. So, first one is sine of theta. So theta is just a generic term for any angle. The sine of theta is equal to the opposite length over the hypotenuse length. Okay? So if we're looking at a triangle here, okay, a right triangle, and if this is theta, the side opposite of theta is called opposite. The side right next to theta is adjacent, because that's what that word means. And then hypotenuse is always the long side. Okay? So you're going to have to memorize these names so we can do this right angle trigonometry. And then CA is the cosine of theta is equal to the adjacent over the hypotenuse. Okay? So that would talk about the ratio between this leg and the hypotenuse. And cosine tells your calculator, hey, I'm looking at ratios. And when it gives you, when you punch in your angle, then it'll give you this ratio. Because if I had a triangle like this, there's going to be a ratio to sides, right? If I have, and as long as it's a right triangle, if I have the same theta, if I make my triangle bigger, the ratio to the sides is exactly the same. Okay? Or, if I make it even bigger, the ratio to the sides is still exactly the same. Okay? So I'm not sure who came up with this idea, but it's been around for a long, long time. I have my guesses. I think that this was the first one, because it's easy to measure opposite and adjacent if you're a builder. It's the hypotenuse in the air that could be hard to measure. But then tangent is going to be tangent of theta is equal to opposite over adjacent. Now this opposite adjacent thing, that is according to the angle. So let's just say that I say that this is theta. If I rename that, then this guy, that side's opposite, and this one is adjacent. So it always has to do with where my angle is. It's not like the right side is always opposite or the left side is always opposite. It's according to the angle. Okay, so with that then, we can start to see how this trigonometry works, since the ratio is always the same. When I was in your seats, there was a table in the back of the book that would give you ratios for angle. But now your calculators have it in there, you just have to tell it to do it. So how would we use this? I'll show some examples here in a bit, but I want you guys to make sure that you find your cosine, sine, and tangent buttons on your calculators. And then while you're doing that, I also want you to find inverse tangent, sine, or cosine. And you'll be able to see that it'll either be like this as a button, or it might be this as a button, and there's probably another way to do that. It's probably a second function. Because we're going to use that to go in reverse to find the angle. I'm going to show you examples on how to do all this stuff. But first, check your calculators, make sure you find that. So here's an example of a calculator here. And the first thing you want to check for is this. Make sure that your calculator is in degrees and not radians, because we're using degrees as our angle measurements. If we used radians, we could have it radians, we'd need to. But here's the cosine button, here's the sine button, here's the tangent button. Okay, now on this calculator, if we wanted to do the inverse, it looks like right there is the inverse. And now you can see all these buttons have changed. Oops. Now they look like, well, mine says sine to the negative first, cosine, and tangent to the negative first. You probably have to do a second function on your calculator. Okay, so it's good to know that most of you have had this already. Here's some examples. So in this first example, and all these notes are online too, but in this first example you can see that I have a hypotenuse of 64, and that's this piece right here, and I've got an angle of 37, okay, and I'm trying to figure out side 1 and side 2. Now, if you have two of anything, like if you have two sides, you can use a squared plus b squared equals c squared to find the third, and then you can find angles if you have two sides too. So if you have two pieces of any triangle, you should be able to solve for all the other pieces. Keeping in mind that, you know, these two are going to be complements, so that'd be like 53, right? Because they have to add up to 180, we know the right triangle is 90. So this is how you do it. Sine is equal to opposite over hypotenuse, so the sine of 37 times hypotenuse then equals opposite, and you come up with 38.52. Let's see if you can put that into your calculator and do that. Okay, let's see if you can solve for side number 2 then. You know, everyone's successful here. That's good. Now look at number 5 here. It says I want to add this. This is not all x's and all y's, it's x and y's, right? So I can't really do math with that. Plus this, that's not x's or y's either. Plus this, okay? This would be kind of the graphical method. If you had perfect graph paper and perfect graphing skills, you could make sure all these angles are perfect. And then you could draw this resultant in, but we don't do that. I mean, someone might ask you to do that sometime, but it's not reliable, no matter how good you are. So what you need to do to solve, you make each vector a right triangle, then determine x and y values, and then add all those together. Okay, so if I was to solve this right now, I would figure out what that is, figure out what that is, figure out that, and that, that, and that. And then so this piece here, it'll be a little x, plus that is a little smaller x. This x is going in reverse, so it'd actually be like that. So my resultant of all these then would be that. So all these three x's put together would equal a little one to the right. And then we have these y's here, so we have first y, the second y is a little bigger, and then the third y is like that. And then after I put all those pieces together, then I could finally do a squared plus b squared equals c squared. And then I'd have to find the angle. And that's probably the stuff that you do in pre-calculus, which you'll do here too. Okay? So, let's see if you can add these two together. Okay, so we got 10 at 30 and 10 at 60. Okay. Okay, let's see if you guys can put these two together now. Okay, so maybe the best way for beginners is to make an X and Y chart. And I would do this because if we put together, 5 or 6 different vectors, well, we'll be needing to organize that. So the first one here is going to be in this direction from the red vector. You agree? And then the second one from the y vector is going to be in this direction. It's going to be shorter though, looks like maybe a little bit, right? Oh, I'm sorry. That'd be the x. Okay. So in order for me to solve that, then this is going to be the cosine. So the cosine, this is for the red one, cosine of 30 times 10 is going to be equal to 8.66, and I have it signified in the right direction, so I'm going to start my new triangle over here. Is 8.66 correct? 8.66, that's from the red one. Now, my red y then, is going to be the sine of 30 times 10, which is going to equal 5. Okay? So I'm going to put that, I'm not going to add that in yet. And then if I look at the y part of the, well, that was the y part of the red one. If I look at the green part, or the x part of the green one, I'm going to have to do cosine of 60 times 10, and that's going to equal 5. And the y of the green one is going to be sine of 60 times 10, and that's going to equal 8.66. Okay, so now I have all my individual pieces, and I have labeled them in their direction, which is very important, because if I don't do that, I won't know if I should add them or subtract them. But in this case, they're all added. So the green piece in the x direction would be 5 here. And then if we do the y of the green, that's going to be 8.66. And then the y of the red is 5. So now we have these two sides here is 13.66, both of them, 13.66. And then 13.66 squared plus 13.66 squared, take the square root of that, and you guys get the actual resultants. Okay? So that number is, so it's 19.32. And then we have to put at an angle. So when you are defining an angle for a vector, you always define it from the resultant's tail. But when you tell someone where to go, you point in a direction, so you give them an angle. You don't say, hey, go out to a spot and when you look back, you'll see me at an angle. That's what happens if you label that angle. So you never do it. You always label a vector by its tail. So in this case, it would be at 45 degrees. And that's not even good enough. So you have to give it an orientation. So it would be above positive x. And so all of this together then is the answer for that vector addition of those two vectors. Okay, and then here's the notes on how I actually did that. You can see what I did on the page 2. But here's some solid notes for you too. That might be a little more clear cut. But notice here, when I was doing my solving, and I knew that I didn't have the final answer, I kind of bubble my pieces that I'll use. And I always include that direction. Because if they were in the opposite direction, then you would have to subtract the two numbers instead of add them, like we did for this one. Okay. So let's look at this, finding theta. Okay, so inverse functions, finding theta. So, if we look at this first example, you can see that we have leg sides of 6 and 7. Okay, so 6 here is the opposite, right? 7 is adjacent to the theta. So you just start out with TOA, because you're using opposite and adjacent. You put in your ratios, and then you're not dividing by tangents, because tangent is just a function, it's a ratio. But the way that you signify this algebra is you put tangents to the negative first. And when you put that into your calculator, you're saying, hey, I got a ratio for you, can you tell me the angle? So you go, so in order to solve for this, in your calculator, go ahead and put 6 divided by 7, and then push inverse tangents, or second function inverse tangents, second answer, or something like that, and see if you can come up with this answer. Okay, so let's try again here. This time, though, we don't have opposite and adjacent. We have adjacent and hypotenuse, so that's c. So the cosine is equal to the adjacent over the hypotenuse here. Let's see if you can come up with this answer, 36.87. Okay, so it looks like you guys are good at that, and you found this probably as well. So then to address the last question, labeling theta. So the first thing you have to make sure you do right is you put the tail of the vector at an origin of a grid, an XY grid. And you always label theta from the tail of the resultant. So the pictures that are associated with that are this. Okay, so here's my vector, right here, okay? So notice I put it at the origin of a grid, the tail, and if I'm labeling this theta, then you can see that it's above what we call positive x. Does that make sense? Now, if you want to, you could label 360 degrees as well. So the first 90 stops here, 180, 270, down to 360. I've seen people do that. And in math, you probably need to do that. But in this case here, we have a vector that is going up and to the left, so that angle then is above the negative x. Does that make sense? Okay. And of course, here's the other one. If we're labeling this vector right here, that would be to the right of negative y. Now, I just told you 3 of them, but there's actually like 8 labels. But I think you can figure that out, right? To the right or the left of negative positive y, above or below negative or positive x. Any questions on that? Okay. Well, let's practice then.